Welcome students to the 7th lecture on fuzzy sets, arithmetic and logic. As I mentioned in the last class that from today I will start fuzzy arithmetic. In my very first lecture, I have introduced you to the concept of fuzzy arithmetic. It is very relevant for solving many practical problems. For example, suppose for a job one needs say about 10 laborers and each laborer will be paid say about 200 to 250 rupees. Now, if one has to budget, then one has to multiply one fuzzy number about 10 into another fuzzy number which is about 200 to 250 rupees. How can you compute those values if those values are not precise? In those cases, you will have to resort to fuzzy arithmetic. In particular, for this problem, you will have to resort to fuzzy multiplication. So, in today's lecture and in next few, I will be discussing mostly on fuzzy arithmetic. As a first step, we need to define fuzzy number. So, what is a fuzzy number? From my earlier discussions, you understand that expressions like about 100, close to 200 or near about 10,000, all these are fuzzy expressions. Representing some fuzzy number. So, what is a fuzzy number? Definition: a fuzzy number A is a fuzzy set defined over R, that is the entire real line, with the following properties. One, the fuzzy set is normal. A fuzzy set say x is said to be normal if there exists x such that membership of x to the fuzzy set x is equal to 1. That means that there has to be at least one real whose membership to the set is 1, or it has a full membership to the fuzzy set x. The intuition is that when we are discussing a fuzzy number say about 10, then intuitively the number 10 should have full membership to the fuzzy set. Similarly, if we say about 10 to 12, then the interval (10 to 12) should have full membership hence, intuitively we can feel there will be certain values whose membership to the fuzzy set has to be 1, or in other words the fuzzy set is going to be normal. Second assumption, the support of the fuzzy set is bounded. Mathematically, zero plus of A is bounded, or in other words, the support for a fuzzy number cannot be infinite. Intuitively, the support of a fuzzy number depends on the problem we are dealing with. Example, when we buy a gift, of about rupees 200, then as we discussed earlier, the support may be say 180 to 225. On the other hand, when someone buys a car of about 5 lakhs, the support may be say 4.75 to 5.4 lakhs. So, the fuzzy set, if you look at in real values, is actually has a much wider support than the one that we have discussed with respect to example 1. So, in this example, we find a much bigger support. We can like that go further, and we can feel that as the values that we are dealing with are bigger and bigger, the support also can be wider and wider, but it cannot be as wide as minus infinity to infinity. So, the support for a fuzzy number is bounded. The support is bounded means there exist real numbers W1 and W2 such that in the interval minus infinity to W1 and W2 to plus infinity, the membership is 0. And the third property is all alpha cuts of a fuzzy number are closed intervals. That means alpha A is equal to sum x alpha to y alpha for all alpha belonging to 0, 1. This comes due to more from practical perspective, because it allows us to do fuzzy arithmetic on alpha cuts based on closed intervals. And this is a fairly established technique in mathematics, as we will see later, that instead of working on functions, if we work on alpha cuts, our calculations for different arithmetic operations like plus, minus, multiplication, division, exponentiation becomes simpler. The question is, how can one check that all alpha cuts are actually closed intervals? as there are uncountably many alphas even in the small interval 0 to 1, it is not practically possible to check for all alphas whether the corresponding alpha cut of a fuzzy number is indeed a closed interval. So, the following theorem gives us an equivalence between fuzzy numbers and membership functions by identifying the nature of the membership functions corresponding to a fuzzy number. So, what is the theorem? Theorem, let A be a fuzzy number, then membership of X to the set A can be characterized as follows. Mu A x is equal to 1 on some interval a b. It is equal to a function L x for x belonging to minus infinity to a and R x for x belonging to b to plus infinity, where L x and R x have the following properties. L x is a monotonically non-decreasing function in the interval minus infinity to a and there exists a number W1 such that minus infinity less than W1 less than equal to a, on which less than a on which L of x is 0 and L is right continuous. So, diagrammatically if we look at it, it is the following. So, there exists an interval a to b on which the membership function is 1. There exists a point W1 such that from minus infinity to W1 the membership function is 0. In between it is a monotonically non decreasing function. That function need not be continuous. There may be discontinuity. Say for example, the function may be something like this. When there is a discontinuity at this point, but in that case the function has to be right continuous. Suppose this point of discontinuity is called x naught, then if we take any sequence of points in the interval coming to x naught from the right hand side, then the limit of those values is going to be the value of the function at x naught. So, this is the characterization of L x. What are these? It is a monotonically non decreasing function. It has to be 0 in the interval minus infinity to W1, and between W1 to A it is monotonically non decreasing, but it is right continuous. In a similar way, we can characterize the function R x. So, there will be a value W2 such that in this interval W2 to plus infinity, the value of the function is 0. Between B to W2, it is monotonically non increasing function, but it is going to be left continuous. It need not be continuous, but if there is a point of discontinuity, at least suppose y naught is a point of discontinuity, then it is left continuous on at y naught. That means, if you are approaching y naught from the left side, we will find that the limit of that sequence is same as the value at y naught. So, this side is called R x. So, characterization of R x is R x satisfies the following: in W2 to plus infinity, R x is equal to 0. In B to W2, R x is non increasing, and thirdly, R x is left continuous. I now give you a proof which establishes the equivalence between the definition that we have given and the new definition in terms of the membership functions, and to show that they are equivalent. So, first we are proving in this direction, that is, if A is a fuzzy number, then mu A x satisfies the above conditions. Since all alpha cuts of A are closed interval, the alpha cut of A for alpha is equal to 1 is also a closed interval. Implies there exists an interval A to B such that for all x belonging to the interval A to B, mu A x is equal to 1. So, this part of the characterization of the membership function is proved, or in other words, we will get such an interval on which the value is 1, and that it has to be 1 comes from the normality, and the membership value on A comma B has to be 1, since the fuzzy set or the fuzzy number A is normal. Therefore, this A B cannot be an empty set. Now, let us consider L x, which is defined on minus infinity to A. Since the support of A is bounded, there must exist a point W1 such that in the interval minus infinity to W1 mu A x is 0, because if no such W1 exists, then the support becomes unbounded. Now, to show that Lx is monotonically non-decreasing, this comes in the following way. Since all alpha cuts of A are closed intervals, we know that for any 2 points x1 and x2, any point lambda x1 plus 1 minus lambda x2, that is a point lying on line segment joining x1 and x2, which happens when 0 less than lambda less than 1. So, for any point lying on that line segment, the membership value has to be greater than equal to minimum of mu A of x1 and mu A of x2. So, let us consider x less than y less than A, where if you remember at A the membership value has been 1 and I am looking at 2 points y and x such that y lies in between A and x. Therefore, by the above property, membership value of y has to be greater than equal to minimum of membership value of x and membership value of A, since mu A x is less than 1 and mu A is equal to 1. Therefore, mu A y is greater than equal to mu A x, implies as I am going from x to y, the function is non-decreasing. In W1 to A. The question is why membership of x to A is less than 1. Suppose mu A x is equal to 1, but if possible, there exists some z such that x less than z less than a and mu a of z is less than 1. In that case, we shall have the following situation. A to b it is 1, at x it is again 1, but in between the membership function has come below 1, but again it picked the value 1, and therefore, we shall have such a situation, and in that case the one cut of A is not going to be a closed interval. Because it will come, the interval A to B will come in one cut of A, at the same time the value x or maybe some interval around x will also be in one cut of A, and therefore, one cut of A is going to be at least union of two different things, which is not a closed interval. Therefore, what we have seen, the following: A on A b mu A x is equal to 1 for all x less than A, mu A x is less than 1, and similarly for all x greater than B, mu A of x is less than 1. Therefore, as we go to x from right hand side, the membership value is less than 1. Similarly, on this side also the membership value is less than 1. See, we have seen that on minus infinity to w 1, for some w 1 here, for some w 1 less than equal to A, mu A x is equal to 0. In a similar way, there exists w 2 such that w 2 greater than equal to B, and on w 2 to plus infinity mu A x is equal to 0, that is after some point it is 0 and from here it is 0. D, we have seen that in w 1 to A, the function A L x is non decreasing, in a similar way one can show that on B to W 2 the function R x is non increasing So, now we show that L x is right continuous. Suppose not. L x is not right continuous. So, let x naught be a point of discontinuity. So, let us consider the situation. This is A, L x is coming like this. Suppose x naught is a point of discontinuity and we have the L x function like that. Now, L x will be right continuous at x naught if the following happens. We consider a sequence of numbers x 1, x 2, x n such that each x I is less than a and limit n goes to infinity x n is equal to x naught. So, we have A here, we have x naught here, and we are looking at points which are limiting to x naught from the right hand side, and these are their corresponding values of L x. So, if L is not right continuous, then for such a situation limit n going to infinity L of x n is not going to be L at x naught, because if the sequence x 1, x 2, x n is converging to x naught and the limit of their functional values is converging to the L at x naught, then it is right continuous. But we are assuming that it is not right continuous, therefore, this limit is not equal to L of x naught. And since L is monotonically non decreasing, therefore, the value at x naught is going to be somewhat less, implies that L at x naught is less than limit n going to infinity L of x n. Suppose limit n going to infinity L of x n is equal to alpha, implies alpha cut of A does not contain x naught, but all x I x 1, x 2, x n belonging to alpha cut of A, implies alpha cut of A is not a closed interval. Then it contradicts that. A is a fuzzy number. Because we started with A is equal to fuzzy, A is a fuzzy number, and we wanted to show that all the characteristics of the membership function should hold, and if the right continuity does not hold, then we contradict the fact that A is a fuzzy number, implies L is right continuous. In a similar way, we can prove that R is left continuous. That is, if we have such a situation, this is A B, and if there is a point of discontinuity, say y naught, then we will find that for any sequence converging to y naught, the limiting value of R x is going to be R of y naught. Therefore, R is going to be left continuous. So, this proves the necessity part of the theorem. Now, we need to prove the sufficiency That is, we need to show that if for a fuzzy set A defined on R the membership function satisfies the conditions mentioned in the theorem, then it is a fuzzy number. Okay, students, I shall prove this sufficiency in my next lecture. Till then, you try to go through the proof again and try to understand the implications of these properties, how the simple three properties of a fuzzy number leads to this analytical property of the membership function for a fuzzy number. So, in the next class, I will prove the sufficiency, and also I will start the basics of interval arithmetic, so that in my subsequent lectures, when I do arithmetic on fuzzy numbers, I can understand how they are carried out to solve numerical problems for involving fuzzy numbers. Thank you.